In this video, we're going to learn how to write down the electron configuration of atoms of different elements. In IGCSE, you've already seen these type of questions. Write down the electronic configuration of sodium element, potassium element, and so on. Sodium has 11 electrons, and at IGCSE level, it was enough for us to simply write down 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the outermost shell. But A levels, because we learned about principal quantum numbers, major subshells, atomic orbitals, the syllabus expects us to write more details, which is going to look like either this, the box notation, or this. These are really not complicated. There's only a few rules that you have to remember and a little bit of practice, and you'll be able to do this very easily. Ground state simply means the most stable electron configuration of an atom, which has the lowest energy, which means the simplest electronic configuration you could write of a sodium element here. Now, in order for us to know how to write down the electron configuration, we need to know how the electrons are filled first. The first principle that you need to know is called Aufbau's principle, where it says electrons will fill the lower energy orbitals first before moving up to higher energy orbitals. Let's see here. We have potassium K19. If we write down the electronic configuration here, it would have been 2 dot, 8 dot, 8 dot, 1. How are we going to fill it? We will first fill the lowest energy level, which is closest to the nucleus. 1 electron, 2 electrons. At principal quantum 1, we're going to fill in 2 electrons here. After that, we will move to a higher energy level, which is n equal to 2. We need to fill in 8 electrons, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. After that, we move to a higher energy level, which is principal quantum 3. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Then we fill the highest energy level, 1 electron here, and 1 electron here as well. It would make sense to you now that n equals to 1 would have the lowest energy, and as we move upwards, principal quantum 2, 3, and 4, the energy increase. Let's take a moment to recall this information. Principal quantum 1 would have only S subshell, and because it's in principal quantum 1, we're going to call it 1s subshell. Principal quantum 2 would have S subshell and P subshell, and because it's in principal quantum 2, it'll be 2s and 2p, and you'll be able to guess how it works for principal quantum 3 and 4 as well. S subshell will only have 1 atomic orbital, P would have 3 atomic orbitals, D would have 5 atomic orbitals, and that is why we'll be able to translate this energy level here
to the more
detailed diagram
subshells here.
Remember that each box represents an atomic orbital. One of the weird things that you're seeing here right now is 2px, 2py, and 2pz. Don't think too much about it until you have come across the shape of subshells in a later video. But right now, just understand that if we have a 2p orbital, and since 2p has 3 atomic orbitals, it will be different. It will be divided into 2px, 2py, and 2pz. To fill in the electrons, we start from the lowest energy level. We're still using potassium 19 as an example. At n equal to 1, there's 2 electrons, so the first electron will be this. The arrow represents the electron. It's not drawn as a full arrow like this, it's drawn like this. Another electron that we're going to draw is going to be in the opposite direction because we are following the second rule that you should know. Hund rule says that electrons in the same atomic orbital must have opposite spins to minimize repulsion, meaning that it will be wrong to draw them like this. The second electron that you draw in the same atomic orbital must have an opposite spin to minimize repulsion. So we've completed n is equals to 1. Let's fill in a higher energy level. The 2p subshells would be at a slightly higher energy level than 2s subshells. That's why we're going to fill in 2s first. 1, 2. Now, at n equals to 2, we still need to fill these up. Most students would make the mistake of filling them up this way. 1, 2, 3, 4, 5, 6. That is completely wrong because we're going to see another Hund's rule here. Every atomic orbital in a subshell is singly occupied before any orbital is doubly occupied. It simply means that if you have atomic orbitals at the same energy level, each of the atomic orbitals should have one electron each before any atomic orbital can have 2 electrons. It should be this way. 1, 2, 3. Only when they are all occupied by a single electron, then we can fill the opposite electrons here. After that, we move to a higher energy level, 3s2, so it will be 1, 2. We move on to the higher energy level, 1, 2, 3, 4, 5, 6. We've come across an exception rule here. The 3D atomic orbital has a higher energy level than the 4s atomic orbital, and that's why the 4s will be filled first before the 3D atomic orbital. So we're gonna fill in 1 electron at 4s. Then you can add up the electrons to see if you've got it right. So you have 2 electrons here, 2 electrons here, 6 electrons here, 2 electrons here, 6 electrons here, and 1 electron here. If you add it all up, you would get 19 electrons in potassium. Now, how do we write the ground state similar to the one that we see at the beginning of the video? Well, it will start with 1s2, 2s2, 2p6, 3s2, then 3p6, then 4s1. In the exam, you are asked to write down the ground state or the electron configuration. I'd highly suggest you write down the details like this instead of summarizing them as 2p6. Just write down 2px2, 2py2, 2pz2, and for any p atomic orbitals, do the same thing. Let's say the examiner is asking you to write down the ground state of O8, which has 8 electrons. 2 electrons in the first, then another 2 electrons. And now you have filled in 4 electrons, so you're left with 4 more electrons to fill in. How are you going to fill them up? It's not going to be 1, 2, 3, 4. This will be totally wrong. Instead, your correct answer should be 1, 2, 3, 4. If you were to write down the electron configuration of it, this is how it's going to look like. 1s2, 2s2, 2px2, 2py1, and 2pz1. Notice that if you have filled this in without following the Hund's rule, this is the answer that you would have ended up with, and you would have been deducted marks for that, because there's a shortcut that you can follow, which we call the diagonal rule, to make this process much easier. So what you're going to do is you're going to write them out in series. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. After that, you're going to draw diagonal lines like this. The electrons are going to be filled in series following these diagonal arrows. For example, this would be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s1 here. Make sure that you're adding up the number of electrons that you have written to always make sure that you didn't make a mistake there. This will be 2 plus 2 plus 6 plus 2 plus 6 plus 1 equals to 19. Another shortcut that you will use to do this is by using the periodic table. In the periodic table, each period will refer to the principal quantum number. Group number 1 and 2, including hydrogen and helium, are called s-block elements. Group 3 to group 8 elements are called p-block elements. The transition metals are called the d-block elements. Now we want to write potassium-19, which is here. So we have to start from here and go all the way here to get to potassium. So this is how we're going to start out. 1s1, 1s2, 1s2. Then we have 2s1, 2s2. So it's going to be 2s2 here. Then afterwards, we're going to have 2p1, 2, 3, 4, 5, 6. 2p6. Then we'll have 3s1, 2. Then we'll have 3p1, 2, 3, 4, 5, 6. Then we'll have 4s1, which is potassium that we want here. This trick is especially useful if you are trying to find what is going to be the outermost electron shell. Because if you're going to write down the outermost shell of potassium-19 here, first we just have to see in which period it is. So it's in period 1, 2, 3, 4. So it's 4 here. And since it's an s-block element, we write s here. Then it's the first of its period, so it will be 4s1 here.